All right, so let's get started. So last week was a little bit of a, shall we call it a break from the normal routine. So it was a couple of guest lectures. I hope you enjoy those, and that you have selected now an interesting project or interesting topic for the part 3 of the project. So now we will go back to the normal routine and talk a little bit about layers, protocols, throughput, and things like that. And so the topic of today is multiple access, and a little bit about random access, and hopefully get a little bit into reservation systems. I'm not sure exactly how far we will reach today. It depends a little bit. But to refresh our minds, we talked now for some time about retransmission protocols, ARQ protocols. And the idea here is to use an unreliable service to provide a reliable service to the layer above. Reliable in the sense that no frames, no packets are lost, and that they are delivered error-free in the right order. And we talked about different types of ARQ protocols, but the transmitters and receivers can put in this general form, essentially, that the transmitter maintains a send window. It's basically a buffer where they can put service data units from the layer above, and that the send window has a certain size. And when the send window is full with the SDUs, it blocks the layer above it. But as long as there is space in the send window, the transmitter accepts service data units from above and attach a sequence number to it and put some error correction code bits on it, and then transmits that and starts the timeout. And if an acknowledgement is received, then that space in the send window is freed up, so it can be filled with a new service data unit from above. If no acknowledgement is received in time, then basically we retransmit that frame. So that's the transmitter essentially. And depending on the size of the window here, we can have more, one or several frames in transmission at the same time. The receiver maintains also a buffer. Now the receiver gets frames from the layer below. And then it inspects those frames, and if it's error-free, then it puts that into the buffer, that is the receive window, if there is space for it. And if it's not space for it, it discards it. It simply throws it away. Whether there is space in the buffer depends on the sequence number of the frame it gets from the layer below. Because if the frame number is such that it fits into the receive buffer, then it's placed there. Now, the oldest frames in this buffer, if they arrive, then they can be delivered up to the layer above it, because then they are delivered in order. So the receiver tries to deliver frames in order. If it gets a frame which is out of order, it temporarily stores it in the buffer until it receives the frames that should precede that. Okay, and basically we do that. And of course one sends acknowledgements to the transmitter to inform that frames have been successfully received. Then stop and wait has a send window and the receive window of size 1. So that's the simplest one. Go back n has a send window which is larger than 1, but the receive window which is equal to 1. And selective repeat has buffers which are more than 1 frame long at both ends. And then, of course, there is a little bit of change in logic, but that's the smaller changes, just to make it work. So that was about the retransmission protocols. And then a detail which I forgot to mention actually last time, which is quite important, is that typically data is not flowing only in one direction from A to B, but also from B to A. So we have 2 parallel retransmission protocols running, one which goes in this direction, one that goes in the other direction. Now, to save a little bit of efficiency, or to make things efficient, when we transmit a data frame from A to B, a data frame here, So this carries now a service data unit, which is supposed to be delivered up to A here. If we, on the same time, have service data units going in the other direction from B to A, like this. So this is the data flow, right? Service data units goes from A to B, and service data units goes from B to A. And in the retransmission protocols, we also have control frames, acknowledgements going in the opposite direction, right? So there is some, if this service data unit comes up here and is successfully received, then we should send an acknowledgement to that in the other direction. And what we can do then is that we can piggyback that onto a service data unit that goes in the other direction. So we can put in the acknowledgement here. Okay, so it takes, we don't have to send a separate frame, acknowledgement frame. We piggyback that onto a information frame that goes in the other direction. So this is called piggybacking. The alternative would be to send an acknowledgement frame by itself, like this. This is less efficient because then we have to send two frames, right, with all the overhead that comes with sending a frame, headers and things like that. Okay, so this is called, oops. So we don't want to do that, right? We want to do, be efficient, so then we use piggybacking. And then, of course, the acknowledgement goes in the other direction, piggybacked on the service data unit that goes the other way. Okay. So these are two parallel ARQ processes that works like this. And we're trying to save up the number of frames that we actually are transmitting. Okay, so that is piggybacking. Now, performance metrics for ARQ protocols has to do with how efficiently we are using the layer below it. Okay, so if we are a retransmission protocol in a certain layer, we have a layer below us that provides a certain data rate, R bits per second. And then we are delivering a data rate to the layer above it, which is the effective rate. And the effective rate is the number of bits, service data unit bits, which can be transmitted per second. Okay. So we have a data rate below us, a data rate that we deliver to the layer above it, above us. And obviously, the data rate cannot be more than what we have below us, right? Because it's the layer below us that actually do the transmission. So there will be a loss, typically, and we want to make that loss small. Or the other way around, we want to be efficient so that the loss is small. Okay, so in words, now in equations. So for a stop and wait protocol, for instance, a transmission of a frame is initiated at some time, and then the data frame is sent. There is some processing, and an acknowledgement is sent back, and then that acknowledgement is processed. So it takes from this point in time to this point in time before the next frame can be transmitted. Right? So if we keep on transmitting frames as fast as we can send one frame every t0 seconds. Okay? So then the effective rate, if there are no errors in the frame here or in the acknowledgement, so under ideal condition, error-free conditions, then the effective rate is the number of upper layer bits, which is the number of upper layer bits in this frame, divided by the total time it takes to transmit that frame. And the number of upper layer bits here is that the total number of bits in the frame is NF. Out of those, NO is overhead bits. So the useful bits, the bits from the layer above, is NF minus NO. So the effective rate is NF minus NO divided by T0, the time it takes to deliver that frame. Okay, and then one can calculate the efficiency, which is the ratio between the effective rate and the data rate of the layer below us. And then we get this type of expression. So we talked a lot about that expression, so I'm not going to go into the details here. But there are certain things here that makes this protocol inefficient. Now, if we also have independent frame errors, some of these frames will have to be retransmitted. So taking that into account, we calculated the effective rate for stop and wait when we have a frame error probability of PF. So when PF is large, then 1 minus PF is small, and then the effective rate with errors becomes quite small compared to the effective rate when we have errors. And the same thing goes with the efficiency. Okay, so we did these type of calculations. We did that for stop and wait, and we did that also for go back n, and then we got this expression for the effective rate and the efficiency. And then for selective repeat, we got these things. Okay, so I'm not going to go into the details here because we did that last time. So, but the overall conclusion is that stop and wait works well for small delay bandwidth products. That is when, let's see, do we have a delay bandwidth product here? Let's go back. It's when this factor here, this term, is small. Okay, it basically has to do with the ratio between the data rate, the propagation delays and processing delays normalized with the frame length in bits. So for small delay bandwidth products, stop and wait works well. Go back n works well also for any delay bandwidth product as long as the frame error rate is small. Okay, and then selective repeat works well for any delay bandwidth product and is less sensitive to frame errors than go back n. Okay, so no delays, no errors, go with stop and wait. If there are also delays, go with go back n. On top of that, if there are many errors, go with selective repeat. Okay, which one is the simplest to implement? This one. Which one is the hardest? This one. Okay. Okay, so that was a short recap of retransmission protocols. And then we started to introduce the notion of media access or medium access. And medium access control is a sublayer just above the physical layer. Okay, so we have the physical layer here. And the physical layer is responsible for transmitting bits between A and B. And then just above it, we have the medium access control sublayer, which is a part of the data link layer. Okay. So one could, for instance, have ARQ protocols and things like that could be on top of these, for instance. Or there could be other functionality here. But here, the medium access control layer is just above the physical layer. And what it does, it regulates the access to the physical medium, which is down here, which could be like a cable or a fiber optical thing or a radio channel, something like that. And the reason why we want to control the access to this medium here is because this medium could be shared by other transmitters. So there could be another protocol stack here, which is also connected to this, with the physical layer like that. And then on top of that, there is a MAC layer. And these MAC layers here needs to negotiate access to the medium such that the medium is not, so signals are not colliding on the medium. Right? So for instance, one can say, now it's my turn, okay, so I keep quiet. Now it's my turn, okay, so I keep quiet. Right? Something like that, some type of negotiation. Because we cannot use, I mean, it's like if you want to have a conversation that everybody speaks at the same time. Sometimes that works well, sometimes not. So in this case, it does not work well. Okay. So that's the gist of medium access control, is to determine how to share a common medium. So there are different rules for doing that. One can divide these protocols in two main categories. One which is static channelization, and here we divide up the access to the medium on a long-term static behavior. So for instance, this one knows that I can use a certain frequency channel forever. So think of this as maybe your favorite or radio program like P1 FM radio, for instance. We know it's going to be on a certain frequency, and it's going to be there forever, more or less. And then P3 here is on some other frequency. Or one can do dynamic medium access control, where we assign resources on demand, typically on a shorter time scale. Okay. So that would be typically if these are two computers sharing an Ethernet or something like that. It's not always that a computer has something to say, but when it has something to say, it would like to use the medium, the full capacity of the medium. Okay, and then, so these dynamic MACs, we want to look at those in some detail. And these can then again be divided into two main categories, those who are scheduled and those who are called non-scheduled or random access. And basically it has to do with the level of coordination that we enforce on this. So scheduled is basically could be replaced by careful coordination, so careful sharing of the medium. So we really want to avoid collisions, for instance. While random access here is more loose coordination, which means that we are not so careful. Every now and then there will be collisions, but the upshot on that is that the efficiency might be better for that. That the efficiency might be higher for a random access method than a scheduled access, and that's because coordination costs communication resources. To coordinate several nodes here, they need to communicate, which means that they are using the medium. Okay. So nothing is for free here. Both coordination and data transmission is done over the same physical medium. So that's why we have these categories. Okay, any questions so far?